And I will come back to piston engines probably after 1 hour or 2. Depends how much time it takes to fix the problem. Okay, so this talk will focus on the problem of what's happening when the flame interacts with the wall. You probably remember that we've said many times that the main problem we'll have in real chambers is that the flame will be burning in a confined chamber, and that our first problem will be to make sure that the walls don't die because of that. So flames and walls actually are an interaction which is more complicated than just the problem of the walls surviving to the flames. Of course, the flame will affect the walls. That's clear. But the walls will also affect the flames. And you will see in a second that the interaction, the effect of the wall on the flame is very strong. It's easy to understand. Most walls are cold. If they are cold, the temperature is low. If the temperature is low, the exponential minus TA over T goes to 0. And in other words, if you're a flame, when you come near a wall, your reaction rates will go down. In other words, too, flames will be quenched by walls in many cases. Now, this is also a problem for pollution, because if you quench the flame near the wall, the fuel there will not finish burning, so you will start producing unburned hydrocarbons when you will open the valves, for example, in an engine. In a gas turbine, there's something important also to mention, is that the walls are also related to acoustics. As soon as you try, for example, to cool a wall by adding multi-perforation to the wall, so this is what we do in most gas turbines. The flame tube has multiple holes so that there's cooling air which can come in. That will change the thermal properties of the wall. It will also change its acoustic properties. Because now if you have a sound wave arriving on a wall or on a wall with multi-perforation, the reflection coefficient will not be the same. Now you know, because we've done that during the acoustics course, what the reflection coefficient is. That means that the energy which will be sent back to the flow will not be the same. So that will change the combustion stabilities first. And so when you design a wall and you start drilling holes in the wall, that will change not only the cooling problem, but also the acoustics. If you change the acoustics, you will change the instabilities of the system. Maybe, again, it's not going to be, it's always unstable, it's always stable. What you will do, you will diminish the level of noise in the system. If you diminish the level of noise, I have shown you that yesterday, that will change the flame again. The NOx, for example, yesterday evening I showed that the NOx levels were influenced by the level of acoustic fluctuations. So you see that the walls are actually playing a big role over the whole range of problems here. So I will talk mainly about gas turbines, but obviously you have the same problem for all applications in combustion. Rockets is one example, but also furnaces. Everywhere you have a flame, you have a wall, and so flame wall problems are very important. There's a statement now I'd like to make about these engines, and this is also related to wall. A lot of people believe that in an engine like this one, the efficiency is controlled by the combustion chamber. Actually, it's not. It's not, because in almost all combustion chambers of that type, you burn all the fuel. Everything, 99%. So you cannot increase the efficiency of an engine like this by working on the chamber. All the efficiency is here, in the compressor. And if you go to many companies, it's the case in France, you will have 40 people working on that problem and 400 working on that problem, because the efficiency first is by getting a good compressor. In terms of, being able to get more power of your engine, this is where you get it. So still, there's a few things which must be done by the combustion chamber. And of course, you must be able to keep this high efficiency at all regimes, which may be difficult if you're not at full power. you must limit the pollution. That's the most important thing. So, you know, what's important about a combustion chamber, if you look at that, it's not what it should do, it's what it should not do. It should not create pollution, and then, most importantly, it should not burn the walls. And that's, of course, the main problem. If you increase the pressure in the compressor, you increase the temperature. If you increase the temperature, you increase the temperature everywhere, including on the walls and on the turbine. And that's actually where the combustion chamber plays a role. It is not, the combustion chamber is not there to allow you to increase the efficiency, but it should not stop you from doing that, which is a different point of view. Now, in these tasks which are here, burning all the fuel is relatively easy. You know, you have a very high temperature environment, you send fuel into that. Normally, if your chamber is a little bit longer, you're going to be able to burn everything. If you don't burn everything, you make it a little bit longer, and then you will burn everything. So burning everything is not complicated. Controlling pollutant emission is much more. You know, that was also mentioned here during the courses. Controlling all the pollutants at the same time is not simple. And of course, the number 3 is mandatory. You cannot have a chamber which will burn the walls. I mean, that's the first criterion. You must be able to keep the chamber in one piece. If you don't, then you have this kind of problems. And all the walls in a chamber can have problems. This is one problem related to the injection system, where the flame interacted with these parts here, and then, of course, you kill this part very easily. But there are walls everywhere, okay? What I've just shown you is in the swirler, but you have walls on the flame tube, and you have walls, of course, here for the high-pressure stator, or whatever comes afterwards. And as we said, now you should know that too, temperatures here are more than 2000 K. Even if you add dilution holes here, you hope that the temperature here will not be too much, but if it is more than 1400, 1500, depends on the engine. Of course, if you want to pay more, you can have special metals here which allow you to go to higher temperatures, but still, it's complicated. So the main problem we'll have is make sure that whatever happens for the flame here does not lead to a catastrophic event for that part. Now, we solved already one problem. Because we use swirl, we know that here, this recirculation zone, which is mandatory for flame stabilization, is far from any wall. So this one is okay. But we still have all the walls here, and we have the blades to worry about. So, of course, the first walls which see the flame are really these walls. And these walls here are in a very critical position because they see the highest temperatures. Now, when this happens, you really have to do something for them. Okay, you cannot leave them like this. So you have to add usually multi-perforated plates here. For other walls, every time you add a cooling system, of course, you have to pay for it. You need the air, you need the structure. So you try to avoid having to cool them. And that's, for example, for turbine blades, in an helicopter engine, it's so small that you try to avoid cooling systems. In an aircraft engine, you need to cool them. In rocket engines, you have a different problem. You have the nozzle behind the engine, and this nozzle also easily suffers from the very high temperatures here, and you get holes there too. So that's also a dangerous problem here. And so to control the lifetime of this system, you need to understand what's going on. I just open a parenthesis here. I'm going to talk here about walls which do not burn. It is clear that if you have too much flux to a wall, the temperature of the wall will increase, and at some point the wall itself will start burning. And that normally should not happen. Okay? In a piston engine, in a gas turbine, normally you don't want the wall to start burning. But there are cases where you do, actually. In rocket engine, you use the combustion of the walls themselves to slow down the process. And it's actually the only way to be able to handle such a flow. And in that case, you need to do two things. If you want to study this problem, if you have a wall like this, and you have here very hot gases, and you know the temperature here is going to go up. At some point, you need to worry about catalytic reactions on the wall. In other words, you need to define not gaseous reactions in a gas, but you need to start describing surface reactions, because this is where combustion will start taking place. And this is described, for example, in this paper. Some of you really need to do that. The main problem is that, as you have seen, we already have problems to describe combustion in a gas. So combustion on a surface using catalysis is even more complicated. So I will not describe these things in this talk. I will stick to the cases where the walls remain sufficiently cold that you don't have to worry about catalytic reactions on them. So the walls are going to be handled like inert surfaces and not doing nothing from the chemical point of view. So let's talk first about the walls which are located here. These walls, in almost all chambers, are cooled by using effusion. So what is effusion? Effusion is allowing some cold, well, when you say cold, it's hot already, okay? It's about 700 K because it's been through the compressor. But still it's cold air, and this colder than the gas here. And this air is injected here by small holes, and the idea is to create a film of cooled, let's say cold air, between the flame and the wall. Now the art of this business, of course, is to design these holes. That's a view of an helicopter chamber, and you can see each of these things here is a small hole. The number of holes, the location of the holes, the diameter of the holes, the shape of the holes, the way you built the holes. For example, you could imagine a hole is just, something like this. But it's not. A hole is something like that. And usually it has a shape here. And this shape will control the efficiency. And the first thing you do when you start working on that, we did, for example, a DNS of the flow in one hole. And you see, this is small, okay? This is like 0.2 millimeter, 0.5 millimeter. You see that you have separation here of the flow, and you have a recirculation zone. Here you have another one. It's an unsteady process. And remember that the layer which will be created here, this zone here, is the only protection of the wall. And I think that has been mentioned also here during the courses, that if you have any problem, if you start blocking the hole, there are many ways by which you can block the holes. One of them, which is famous now, is if you fly in the cloud of a volcano, the particles produced by the volcano, they are solid in the atmosphere, but when they go through the compressor, they melt, and they do some kind of very nice, how would you call it? It's like droplets, if you want. And these droplets splash here, and when they splash here, they become solid, and then they stick here, so they just block the hole. If you start blocking enough holes, the film here will be okay in most places, but there will be a few places where the film will actually disappear. If the film, the cool film here disappears, then the hot gases will touch the wall, and that's the end of the chamber. There are quite a few chambers in industry which, when you open them, you see that you have big holes here, and they still work. They can probably survive, but of course it's not the design point you want to have. So that's for the walls which are located here, the walls. Now, if we go to the outlet, we find the turbine. The turbine itself, especially in aircraft, the first part of this turbine is sitting right in front of the gases, okay? So this is a very difficult life. This guy is just in front of the burn gases, and there is a direct impact on it. So those things, in most cases, have to be cooled. How do you cool them? Well, again, you use multi-preparation plates here, and you let some fresh gases go into the blade and then out of it, and so you try to cool all these things. And as I said, it's not only a combustion problem. You cannot hope that you're going to find the temperature in this thing, in the solid, if you don't do something which allows you to couple the flow and the temperature. And this coupling between the two is a complicated problem, which I will describe later today. And as I said too, it's not only about the flame itself or even the heat transfer itself, it's also about acoustics. Every time you're going to start modifying the walls, putting more holes, will change the acoustics, so the engine might become stable or unstable, which will itself also change the flame. So, like always in these chambers, you have to be very careful when you start playing with these things. So, what I want to do now is to start discussing flame wall interaction in general, and you will see that what it really leads us to is to build simulation where we can do the LES of the flow and the heat transfer at the same time. That's the most important thing. And I will give examples then of different studies where wall temperatures play a very strong role on flame, and that we need to include that in our description. It's not, again, something that you do when you study an academic flame, because in academic flames, usually there are no walls, or they are far away. And also, if you look at many models, we talk about FGM, we talked about FPI, all these models begin at line 1. It said the flow is adiabatic, okay? Because it's simpler. But here, if you go to real engine, at line 1, it's written the flow is not adiabatic, you have walls. So that will also make modeling more complicated. I will stick to smooth walls for the moment. So I will not discuss multi-perforation. There are many reasons for that. One of them is that it's already sufficiently complicated. And also the other problem is that multi-perforation is really a touchy topic. So industry doesn't like us to discuss this point too much. So let's start by the general problem of flame wall interaction. Now, in general, if you're sitting in a burner and you have, let's say for the moment, a premix flame in front of you. So you're on this wall here, and here there's a flame. So again, we can take the example of the Volvo case. You have a flame like this. So you see, it's the same process that we had when we were discussing turbulent combustion. If you are here in a zone where you have only fresh gases, life is easy for you because the fresh gases are cool. If at some moment the flame moves up, and it does that in a turbulent flow, and you are in the burn gases now you see a high temperature. So you have to handle a high temperature gas. And there is one moment which is special in the whole process. It's the moment where the flame is just on you. Okay. That's what we call flame wall interaction. That's the worst case of flame wall interaction. So when we say flame wall interaction in general, it really means interaction with cool gases, which is easy, interaction with burned gases, which is more difficult, and interaction with the reacting zone, which is really difficult. So if you plot now the flux at one point here on the wall, you will see then that there will be what we call phase 1, moments where you have a reasonably small flux. It's going to be large, but not extreme. There will be moments where you will have larger fluxes. It's when you are touched by burn gases. And there will be moments where you will have flame wall interaction. That's the peaks that you see here. And these peaks lead to very large heat fluxes. Here we're talking about, fluxes of the order of 1 megawatt per square meter, which is the same fluxes you will have in a nuclear power plant. And so these fluxes are going to be extremely large. And our first problem, if you want to work on this heat transfer problem, is to be able to have an idea of the order of magnitude of all these things. So people have looked at this problem for a long time. And the first thing we did was to look at this phase here. You can build an academic, again, a canonical problem for that, which is called head-on quenching. Head-on quenching is what's happening if you have a wall here, and you have a flame propagating, and then suddenly the flame hits the wall. That's why we call it head-on, because it's straight on, and it's an unsteady problem, but it's one-dimensional. So you can do it in the lab, and you can do it experimentally. And you can do it numerically, excuse me. Now you have a second problem, which is a little bit more complicated, which is called sidewall quenching. In that case, the flame moves in a tube, and it's moving in this direction, and the wall is here, not here. This is why we call it sidewall quenching. So there will be a distance between the wall and the flame where nothing will happen. And then the flame will have this shape here. And this actually happens in all flames, okay? Every flame you create in an engine, piston engine, or in a gas turbine, is going to propagate along a wall, so there will be this kind of behavior. The first thing I would like to repeat now is that since the wall is cold, there must be a region here which is also cold. We haven't said how much, but in this region, no chemical reaction can take place. We will call that the quenching zone, or the quenching distance for this quantity here. And in this quenching distance, no combustion can take place. Okay? This is true here, and it will be true here. When this flame will arrive here, at some point, it will have to stop. So let me show you a simulation that we're going to repeat here. This is a coupled simulation between a wall here and a flame here. So the flame starts around here, and it comes towards the wall. When it hits the wall temperature will increase, but the flame will quench. So look, be careful here, the range of temperature is not the same, okay? You have 10 K in the wall, 1500 K in the gas. The reason for that, of course, is that the wall has much more inertia than the gas, okay? When you send the flame once on a wall, the wall temperature will increase maybe by 10 K. This is why actually you can even put your finger, on a flame. If you don't stay there too long, you won't get any problem because the inertia of any solid is much more than the inertia of the gas. Don't want to repeat that too many times, of course. So let me show you again this movie. So we have here the things we're going to discuss later. This is temperature. This thing is moving at the displacement speed or at the consumption speed. Here it's the same because this is a 1D flame. This is the fuel mass fraction in black. And in blue, you have the reaction rate. So now, when I'm going to play this thing again, you will see the flame coming here. The reaction rate will go to 0 when the flame quenches. And then after that, when everything is quenched, we just have a diffusion problem. The fuel which is left here will slowly diffuse to this side, but it cannot burn anymore. It's just diffusing. And the heat here will slowly diffuse. That means that this point here will actually recede and go in this direction just because it's a heat transfer problem in 1D. So look at this, quenching. The fuel is slowly going down, and the temperature is slowly diffusing. So it really means also that if I track an iso surface of temperature, an iso line of temperature, this point, for example, you will see this point will come here, and then it will come back. Okay. So let me show you that again. Look at this point, it comes here, and then goes away. And so you can really see that there is a distance here where an iso temperature stopped and then went the other direction. The other thing we can do is that during this interaction, as you can see from the wall temperature goes up and then stops going up, and then actually it will slowly go down, which says that there must be a moment where the flux into the wall is maximum. So you can plot all these things as a function of time, and this is what you obtain. So this is the flame position. So this is the distance between the wall and the flame. Since the flame is moving at a constant speed initially, this thing decreases slowly and constantly at a constant speed. And then, there is no radiation, so as long as the flame is sufficiently far away from the wall, the flame does not see what's going to happen, so the flame keeps moving. And suddenly, the flame starts sensing the wall. So what does it sense? Well, it senses that in the preheat zone of the flame, it becomes very difficult to increase temperature because this temperature here is imposed. So when this point arrives here, or let's say when this flame arrives here, it's not possible for the preheat gases to be preheated. And so what's going to happen then is that the flame will stop and go backwards because of diffusion. In the same moment, the flame speed, this is the consumption speed now, the consumption speed will be constant and then suddenly drop to 0 when the flame gets quenched. And the heat flux is 0 initially because when the flame is far away, the wall does not care. The wall is happy. And then suddenly things, the flame gets closer, so the flux goes up, then it goes down again, and it reaches a maximum value here, which is the maximum value we want to measure if we want to look at flame wall interaction. So when people measure the maximum value here of the flux And they do that for different wall temperatures. This is what you obtain. So this is the wall temperature, 300K. They went up to 600. Those are different experiments and different simulations. And those are megawatt per square meters. And you see, at ambient temperature, you get fluxes of the order of a half megawatt per square meter. And when the wall gets warmer, sometimes it's going up, sometimes it's going down. But the trend is that it's mostly going up. It's not so interesting to look at this result that way. From a theoretical point of view, what should be useful is to scale them. And that's what's been done, actually. There's one quantity which is relevant for a problem like this, is the power of the flame. The power of the flame is the quantity we should use to scale the fluxes. It's obvious that if you have a very energetic flame, you're going to generate a higher flux. So this is what's done here in this table. We use the flame power, and the flame power is actually very simple. It's rho multiplied by SL multiplied by the heat release that you can write either Cp delta T, or you can put here Q, the heat of reaction of the combustion. So this flame power is also watt per square meters, and it's a good way to scale the maximum flux. So if you construct F equal to the maximum whole heat flux divided by the flame power, this is what you obtain here for different cases. And you see that all hydrocarbons actually lead to the same value of the order of 0.3, except hydrogen. As always, hydrogen is always special here. So that's a very useful interpretation that if you have a flame in a box, and you can compute the flame power, and that's independent, any box, you can take any pressure, you just compute this thing, you multiply it by 1/3, and you have a good idea of the maximum flux which can ever be found on a wall. Okay. No. Radiation here, we have done simulations with radiation, but radiation is small compared to the interaction of the flame on the wall. If you would add radiation, that would increase a little bit these numbers, but not by much.
So, when you've shown that video, we have seen that the temperature at the wall increases at the maximum, then a little bit decreases.
Yeah.
So the loss is because of radiation, or?
No. It's just because here, if you wait for a very long time, this temperature here will also decrease. The gradients go down. So at some point, you're going to cool also this point. But it takes forever. Let's say here the temperature stops increasing. That would be a better statement. It would take forever to go down until everything gets cooled down. But that will take.
In the distance ahead of the wall, where flame quenches, will keep decreasing as you increase the wall temperature, and when it burns, it is at very high.
Yeah, that's difficult to say. When you increase the wall temperature, you change the chemistry at the wall, and the effect it's difficult to predict. As you can see, sometimes going up, sometimes going down. You need to do the complex chemistry computation or to do the measurement. I didn't say that that's an additional problem here. The only thing you measure experimentally is the flux. They cannot measure anything else because when the flame, I will say that in a second, when the flame crashes on the wall, it's so close that you cannot do any diagnostics there except measure the heat flux. So the heat flux is the only thing we'll have to verify this kind of data.
What I'm trying to say is that the distance between where the flame quenches and the wall, it may keep decreasing as you increase the wall temperature, and when the wall actually burns, it actually reaches.
Well, those walls don't burn, okay? They're not supposed to burn. It's too cold yet. 400K, they're not going to burn. They're going to go from 300 to 310K, as you can see here in the movie. And so that's not enough to have the wall burn. It's only influencing chemistry here. In the wall, there's no combustion. Should not be. Otherwise, we have a major problem.
What should be the boundary condition that we should apply on the wall?
Here it's isothermal, but as you can see, it does not play a role for this first case because the perturbation of temperature has no time to reach this wall. So you can use iso-T or adiabatics the same. If you repeat now this interaction 2 times, 3 times, then it gets more complicated. But here it's only one shot, so you can say constant temperature. No, if it's realistic, it's still going to be isothermal because what you have here is cooling water. And then if you have water, temperature will be imposed at the cooling water temperature. And so if you repeat this interaction many times, then you will end up with a profile which is almost straight. Because on the average, yeah, it will reach a steady state. Again, because it's something I will describe in a minute, the characteristic time of the flow here is 1 millisecond. The characteristic time of a wall of metal is a few minutes. So if you come back after half an hour, you will find a temperature like this. But for the first flame wall interaction, that's what's happening. That's also why it's a cold start and steady combustion is not the same in an engine, because when you start the engine cold, the walls are cold, and so these processes take place like in this picture. If you come back after 10 minutes, then the walls are hot, and it will be a different flame wall interaction. This is why also people plot these curves here as a function of wall temperature. In an engine, the wall temperature can be anything between 50 degrees to 150 or 250. So that's about the range you see here. This temperature. Okay, this one. Here, of course, this is the water temperature. Exactly. That's wall temperature for me is always on this side because that's the hot side. But obviously, this one is much higher than that one, depending also on the size of that. You have to compute the flux with. But here you have cooling water. Okay, so this cooling water is about 90 degrees, 100. It's under pressure. It can go a little bit more than that, but not much more because then after that you have a problem. So here you have about 90 degrees C. So here you're going to have 200. 250, 150, depends. Also, the temperature is not homogeneous in the chamber. It has a complicated shape. Designing the cooling systems of an engine is a business in itself. Okay, you do computations again, and it's not something I want to discuss today. So there's a very simple rule you can keep in mind: is that when the flame touches a wall, it will deliver approximately 1/3 of its power to the wall. And then it will die. Okay. That's the important message there. You can do the same thing for the quenching distance. This is the flame position. So this is the distance between flame and wall. The quenching distance, the distance goes down, and then the flame quenches, and then the isothermal lines here start going backwards. So you have this shape here for the flame distance. And so here you see that there is what we call a critical zone where there is no combustion. This critical zone, which is called YQ, you can scale it and scale it again by the flame thickness, which is written here. So if you scale that, you see that for this quantity here, which is the wall distance, the flame wall distance normalized by this quantity here, which is D thermal over SL0, which is also equal to the flame thickness. This quantity reaches about 3. That means that there's in an engine, you know before you begin that there is a zone near each wall where for approximately three times this quantity, there will be no flame. The flame won't be able to go there. And this quantity is, this is not really the flame thickness. It's an evaluation of the flame thickness. A real flame thickness computed using the exact profiles of temperatures, which are computed like this. I've shown you that last time. It's the TB minus TU divided by the maximum of dTdx. So this is the distance from these 2 points. We call it delta. This delta is larger than this one, about 3 times, which happens to be almost exactly what we have here. In other words, the flame stops when the flame thickness is equal to the flame distance. That's where the flame starts feeling the wall, and that's where things change. So again, that's a useful scaling here. You can just remember that if you know the flame thickness, you can right away evaluate the quenching distance. And so during head-on quenching, the flame will stop approximately 3 flame thicknesses away from the wall, depending on how you define a thickness. Now, that really means that the flame never touches the wall. Okay? So there is no flame wall interaction in that sense. The flame never crashes on the wall. and there is some unburned fuel left near the wall. This unburned fuel will not remain there. If you look at the movie here, you see that after the flame stops, now it's gone, but you see the fuel here just by diffusion is going away. So this fuel will diffuse, it will not burn, it will remain as hydrocarbons. Now, depending on the chemistry, what these hydrocarbons are going to become in a hot gas here depends on the chemistry. In many cases, they stay there. There's a specific example of that which is a little bit different. It's crevices in an engine. In an engine, you have flame-oil interaction here and there, but there's a place where flame-oil interaction is extremely strong. It's here. So here, of course, the flame cannot go through, but this is a place which is fully surrounded by walls, so the flame usually stops there. And it's quite possible when you open the valves here that you see some unburned fuel coming back into the chamber, and that's, of course, for pollution, it's not good at all, especially if temperature has gone down at this instant, these gases may just stay there. So controlling this thing is an important question for them. Okay, so let me move ahead now to the next topic, which is sidewall quenching. Sidewall quenching is more difficult to study. Head-on quenching, you just send a flame on the wall, simple. In an experiment, you can do that easily. Sidewall quenching requires much more sophisticated tools to do it. Here, the flame is propagating in this direction, and the wall is here. But this is the prototype problem of every flame oscillating near a wall, so that will be the case in a rocket, will be the case in an engine or in a gas turbine. In that case, if you do the simulation, you find that the fluxes are smaller, only 1/2 of what you had before. Instead of 0.3, it's 0.15. And the Peclet, of course, it goes the same way. The Peclet are larger. The distance, the quenching distance from here to here is about 7 times the flame thickness. Now, if you look at the turbulent flow, that's an old simulation we did at Stanford. This is the wall, this is the premix gases, this is the flame. You see the flame is here. Then the flame comes closer to the wall. And here we'll have a head-on quenching. But then after this head-on quenching, the flame will go up and down, and here you will have a sidewall quenching. So in the turbulent flow, we expect to have all kinds of configurations from head-on to sidewall, and this is what the DNS are showing. Okay, now let's move to the third case of flame-oil interaction, which is the tube quenching. Tube quenching is basically two times sidewall quenching. You put a wall on top, a wall on the bottom, and you let the flame go through. I've already told you 5 days ago, I don't remember, it looks like it was a long time ago, that when you measure flame speed in a tube, the flame speed was depending on the distance between the two walls. Actually, it depends so much on the distance between the two walls that if these two walls are too close to each other, there is no flame propagation. And this property is actually very, very important. Probably we would not be sitting here without its property, because you will see in a minute how important this phenomenon is. In other words, you can stop a flame if you force it to go through a hole which is too small. What means too small is typically 50 times the flame thickness. So you see for most flames, this quantity delta here, the flame thickness is of the order of 0.1 millimeter. So 50 times that is like a few millimeters, 4 or 5 millimeters. So if you take a tube which is smaller than that in diameter and you send the flame on it, the flame will begin to go into the tube. Then the flame will be cold everywhere, and it will be cooled more and more, and at some point it will be completely quenched. It will have to stop. So this has many, many implications which I want to discuss now. Yeah, but the 0.3 is almost universal, so that's okay. And as long as this wall here is sufficiently thick to keep a low temperature, this will hold, okay? So you don't want, of course, if this thing burns right away, it's not okay. But in most cases, this thing will not burn, so the temperature will be kept low at that point, and that's sufficient for quenching.
So that is sort of equivalent to saying
Yeah, the assumption is that the surface must remain cold. If this thing is very, very thin, but you know, again, that's what I said, the mass of the metal is 1,000 times more than the mass of the gas, so it's very difficult for the flame, especially if it happens only once, it's very difficult for the flame to burn the metal in one shot, you know. It won't happen. You know, the flame will die, but the metal will be okay. If it's one flame, one time, no problem. You can keep saying it's isothermal and it's good. If you don't want to repeat it too many times. So this quenching diameters are very easy to measure. Okay, you just take all kinds of tube, make them smaller and smaller. At some point, the flame doesn't go through them, and this is plotted here. This is the tube diameter you need for quenching as a function of the equivalence ratio. So this is stoichiometric, and of course, remember that we said that before. When the flame is fast, it's easy from this relation. When the flame is fast, it is also thin, okay? And slow flames are white flames. So here, if you have a fast flame, it's going to be thin, so you need a small tube. Okay, you see here centimeter, so that's about 3 millimeter. But if the flame is a slow flame, then it's much thicker, and the scaling of the Peclet tells you, okay, then here, for example, for this flame here, which is a lean flame, you can have a tube of 1 centimeter, and the flame will not go through. So let me show you now two applications. And I think for combustion science, those are really good illustrations of how simple concepts can have very big consequences. The first one is flashback protection. You remember this movie I've shown you of the flashback of the flame stabilized behind the backward-facing step. This is a dangerous phenomenon. There's a way to stop it. You can just put here a grid with holes, which will let the flow go through, but not the flame. That will prevent flashback, because if the flashback wants to begin, when the flame will reach that point, then it will stop. Okay. Here there is no grid like this. If there would be a grid here with holes, then the flame will be stopped here. That's what we call the flame arrestor, and flame arresters are actually sold on the market. You can buy them, because every time I've seen some people doing premix flames here, it's a good idea if you do a premix flame experiment to have a system like this. How does it work? It's using exactly what I said, but it's done in such a way that the tubes here are not only small, they're also long, to make sure that the flame, you know, can go through and not, by some chance, jump on the other side. And the system is also built in such a way that you know these things are not going to burn. Okay, they're going to stay there. And so if you build a premix system, normally you're going to have a burner here. And what most people do, they have here, that's the best way to do it for mixing, okay? You have here a nice chamber where you inject gas and air, and you let them mix here. And then, of course, the problem is that if you have any kind of problems, flashback, instabilities, the flame can go back here and boom. Okay? That's actually very dangerous. You know that if the tube here is small, combustion will take place here at almost constant volume. Then the pressure, this can be a 1 bar system, but if the flame comes here and explodes, you will go to 8 or 9 bars. This thing will go to 9 bars, it will explode, and we'll lose PhD students. Okay? So the way you do that, you put the flame arrestor here. You put this system here on the right-hand side, so that if the flame has the bad idea of coming up here, it will stop. Okay? So that's the first application of flame-hole interaction. Now, just a short story about that. That's what I had in my experiment during my PhD. What we did is we installed this system here in front of my burner, and we just ran it for 3 years. And after 3 years, when we opened this thing and we looked at the multi-perforated hole, it looked like this. Okay, so and there was a big hole in the center, because the problem is that if you do that too many times, you end up punching a hole in the flame holder too, in the plate here. So you need to check. This is why actually they sell these things. These things resist to the flame interaction. And in our case, the grid was too thin, and it died after, I don't know, we don't know how many times, but so we were in danger for a long time. So We didn't know it, so that was fine. Okay, second application. This one is a fun one. Probably you heard about it before. That's the mine lamp. You know that we'll talk about it when we talk about ignition. In a mine, you extract coal, but that's not the only thing you extract. Okay. You have a mine shaft here. You extract the coal, but you also extract gas, mostly, you know, CH4. And if you have enough CH4 in a zone like this, you have air, of course. Let's think we're talking about beginning of the 19th century. You have air, you have methane, and there's another thing you carry with you. There was no electricity, so you carry a lamp. So those people didn't take my course, but you know that if you have fuel and air and a flame, bad things may happen. It's even worse in the case of a mine shaft, because here you may have 200, 500 meters which are confined. You know. And remember what we said about explosions. If you start a flame in a confined domain where you have obstacles and no place for the flame to expand, you're going to go to deflagration, then you're going to go to detonation. And this is a major safety problem. You will see that in a second. So one guy, Davy here, as you can see, you know, 1817, Davy was a lord. He was an English lord. I know you like that here. So, Davy took a patent on this system, and then he wrote a paper on that. And the system was basically this flame that you can see here. The principle is written here. You put the flame to have light, and then around it, you put a small grid, which is this thing here, which is big enough to let the light go out, but small enough so that the flame cannot go out. Okay? And so this is the system which allowed actually the English at that time to start digging more and more without killing people every day, so that people can actually go down, have light, but no problem of flame ignition. Okay. Davy, that's an interesting story actually. It's also the other thing I keep telling, you know, if you have a good idea, you have to be sure that someone got the same idea at the same moment. And in those days, even in those days, there was another guy in England called Stephenson. And the guy had the same idea at the same moment, except he was not a lord. So he wrote a paper, actually tried to take a patent on his idea, which was almost the same design. And then Davy said, well, if you got this idea like I got it, it's because you stole it from me somehow. So I'm going to send you the police, and I'm going to sue you, etc., etc. And of course, the Lord won. Okay. So now everyone knows the name of Davy, but it seems that this guy, Stephenson, there are actually papers which were published in the 20th century about it. They got all the letters from the two guys, they got the papers, and they really think that Stephenson never stole anything. He just got the idea like Davy, you know. It was like an almost obvious idea at that time, but of course, it's better to be a lord than to be a normal citizen, as you know. So that's also now the other thing I wanted to tell you about that. So go back to this problem of mines. And what I'm going to tell you, maybe some of you know the story, but it's not a joke, okay? It's a true story. That's the way we do it. Where we did it, actually. Today, we hope we don't do it that much. So in those days, 19th century, if you started having CH4 in the mine, you cannot work anymore. And usually the boss will say it's your fault, you know, because you guys don't dig the right way, you know. There's something wrong you're doing here. Of course, it's not their fault, but you stop paying them. That's the good trick about it. So someone has to find a way to extract the gas so that you can go back to work. And there was no pump, you know, at that time. And the only thing you can say is to burn it. The only thing you can do is really to burn this gas. There are good and bad methods to burn the gas, you know. The bad method is if you wait until you have an explosion. If you wait until you have an explosion, then usually, you know, everything will be gone anyway. So that's not what you would want to do. And the explosions in mines are not an old problem only. I have here a small list of the people killed. I stopped in 2011, but in China, it's thousands of people every year, okay, getting killed because of that. So we have old pictures, you know, in the 19th century, but even today, if you start having this problem in the mine, of course, you don't have these Davy lamps, you have electricity, but electricity is not good also because electricity can do a spark. And then you have a problem. So this kills people even today. It kills a lot of people. So you would like to avoid that. So there's another way to do it that was used in the old days. The good way would be to control the combustion. And this is where combustion science begins to be really interesting. Say, can you burn this methane here? There's not much methane, you know, it's a few percent maybe. Can you burn it slowly? Well, there's a method to do that. The first thing to say is that most of these gases are lighter than air. So if you wait sufficiently long, they will go up in the mine, and they will be near the ceiling. And so that if you look at it from a combustion guy, you say, okay, if I wait long enough, what I have is a segregated state, like in a diffusion flame. I have air on one side and fuel on the other side. So you might think that maybe you could burn it here, not as you would burn it in a premixed mode, but you could burn it as in a diffusion flame. And this is what I'm going to tell you after the break, because it's 10. Any question? Nope. I'm going to try to fix up my projector problem so that we can also do the piston engines, but I'm not sure how to do that. Okay, so let's move to the end of the story here. So you still have a problem if you know that you have fuel on top here, you have air on the bottom, so you have fuel and oxidizer. You need an ignition source, okay? But everyone is out of the mine, okay? Everyone is on top waiting. So you need to find someone to go down and ignite this thing. So how do you do it? Well, you take the youngest guy usually because he doesn't know about this thing. And you give him a Davy lamp. And first thing you do also, you wait a few hours so that the methane goes up, okay? And so that you really are in a segregated situation. So the guy then goes into the mine. Usually he has to crawl. Why does he crawl? Because at the bottom of the mine there is less fuel. So he crawls there with his lamp. He goes to the place where people have said, okay, this is the place where there is fuel. Then he removes the grid from the lamp so that the flame can get out. And then you raise your hand. Okay? When your hand reaches this zone, normally you start burning the fuel there. Okay? The problem is, of course, if you know combustion, that there are only two solutions there. The first thing is that you really waited long enough and that there was no more fuel generated and then really all the fuel was up there. So when you raise your hand and you bring temperature to that point, you are exactly in the situation of the diffusion flame that you have studied before. And you will ignite something which is nothing less than a triple flame. And it will actually, again, like we said 3 days ago, it will separate the unburned state from the burned state. Here will be on the mixing lines. Here will be on the equilibrium lines. And it will be like a pancake, if you want, of flame growing, and which will slowly attract here the fuel by diffusion, and the fuel will burn in this thing. And it works. It's something which was done in those days. And then when this is done, all the fuel is burned, and you still have air, so you can come back and you can work again. You have to wait maybe a few hours until this thing cools down. Now the problem is that, especially if people went out of the mine fast, and if there is any kind of mean flow field in the mine, then the mixing keeps going. And there is no segregation. So the fuel and the air are not separated. And so then, when this guy walks in with his lamp, it's fine. But when he opens the lamp, of course, then he starts a premix flame. And he dies. But it's okay, because you can always start operating afterwards. So in every case, it works. So that's a good illustration of the importance of combustion science in practice. And you see also it combines ignition problems with flame hole interactions. Okay, let me go back now to normal cases and to this question of fluxes. When we did all the scaling of fluxes, one thing you saw is that this was a high flux, like 1/2 megawatt per square meter, but it doesn't last long. It doesn't last long because the flame dies right away. So after a few milliseconds, this flux goes back to normal. And so what's done in most cases is that we almost neglect this phase here, And we say, okay, the most important phase is really this one. That's the phase where the temperature is high, and basically the points here in this chamber, they are swimming in burned gases. Even if there is no flame, that's tough enough for them. So you can forget, in most cases, this phase here, and really worry about what's going on when the gases are hot. So this is where you have to start working on coupling problems. Because if you want to know now the temperature of the blades here, which are submitted to a gas which is at maybe 1500 K, you need to compute the temperature of the blade and the flow itself at the same time. Now, interestingly, in most companies, there's a department for combustion and there's a department for turbine. And they don't talk too much because they compete for the same money. But if you look at the problem like this, you see that it's kind of difficult to imagine that you can compute the temperature of this thing without computing this first. And the main problem we have today is that the combustion people compute this with runs. They give average temperature profiles to the department of turbine, and the turbine people compute that with a different code using the temperature profile here, the mean temperature. But the fluctuations are gone, which is a bad idea. What we try to do now is what you see on this film. We try to do everything in the same code because the fluctuations are going to be important. So what we need now is a coupling of the codes for the combustion chamber, the turbine, and the heat transfer within the walls. And this is what's going to happen in your generation, that you will see more and more of this type of coupling. Now, this coupling can be what we call weak or strong. Weak coupling means only you take the mean values of one code and you send it to the other code. Take the mean values from the combustion code, send them to the turbine code. The strong coupling would require to do that not only taking the mean, but taking the instantaneous values. And doing that is a much more complicated problem. I will show a few examples now. A few words about parallelization. You know that if you write a code and you want to make it parallel, it's already complicated. But if you do coupling, strong coupling, for example, at the same time, you solve for the LES in the gas and for the temperature in the solid, then you're going to have two parallel codes working at the same time on the same machine. And that means they're going to share the same machine and they're going to have to communicate. So within one code, it's already complicated to communicate. But if you have two codes, or maybe three codes, then it gets really interesting, I would say. Now, one issue which was mentioned before is, what about radiation in this problem? Yes? Yeah.
So do we have to resolve in the wall, or are you using some sort of modeling?
In most cases, we use wall laws.
They're good enough?
Yeah, they're good enough for, well, they're never good enough. That's a good compromise. We use wall laws for that. So radiation, we know that the temperature here is pretty high, and so there's a big problem for people doing combustion is, should we neglect radiation or not? Well, I'm going to show you that it depends what you want to do, but in many cases, you should take radiation into account. And radiation is a pain. I've already shown this slide. This slide is also from the point of view of people doing the blades, where they tell you that they want 25K accuracy. I mean, those guys must be joking. I mean, no one can predict the flame temperature within 25K. I mean, we know that but still, that's what they want. So it's actually, as I said, they want 25K, but then they take a safety margin of 200K anyway. But if you want to compete with other people now, you want to decrease the safety margins, and then you really want to know if you are close to a problem or not. And then you need increased accuracy, and this is where it's good for us scientists that you need better tools to predict that. So I'm going to show you a few examples of coupled computations. One of them is what you need to do first before you do an engine. You need to do academic cases, and those cases come from the von Karman Institute, where they did a lab-scale experiment with small temperature differences to check that you can compute the heat transfer with LES on the blade, for example. And then I will show you an helicopter case from Turbomeca with radiation to show you you can do it also in a real configuration. So that's the famous experiment done at VKI. So that's an example of blade. As we said before, you have the blade and you need to inject cold gases here to cool it. Otherwise, this thing dies. So when you do it in the lab, you don't inject very hot gases. You inject 330 K gases here. And here you have cooling air at 300 K. And the objective is, can you compute this thing? Well, it's a complicated problem because it requires to know the flow field everywhere and the heat transfer everywhere. So the cooling air that you inject here is following strange trajectories, and it's mixing with the hot air coming from the other side. And you need to compute all that. So that's a view of the LES. So there's no combustion now. It's only a heat transfer problem. So you see you inject the air. It's turning right away here. There's a second jet and a third jet. You can see here the mixture fraction, actually. It's the N2 plenum, so it's like the mixture fraction. You see these jets are coming here. This is why we send them here. This is a very hot zone, so we try to protect this zone with these jets. That's the objective of these jets. That's a view of the density gradients. So that's what you will see in the experiment if you would do Schliemann visualization. And that's a result for the aerodynamic part. So I'm not going to go into the details. This is what we call the isentropic Mach, which is like the pressure distribution on the blade. And you can see that the experiments and the LES work very well in that case. Let me jump to the problem of coupling. Here we need to couple the LES in the blade with the flow outside. And as I said, you know, this blade is a massive blade. Its temperature changes over a few minutes, while the flow itself has a much shorter characteristic time. So we need to couple the two. And the way it's done, it's that you couple the two, but basically to make it short, you compute the temperature in the blade for 1 minute, then you compute the flow for 1 millisecond, and you say, this flow is not going to change for the next minute. You come back to the blade temperature, and you advance in time this way. That means you don't try to compute the temperature in the blade on the scale of the flow, because that would take forever. So if you do that, you're able to advance in time much faster, and in that sense, it's what we call a weakly coupled problem. You don't have a consistent solution in time. The solution will be right only after the flow has converged. Because when the flow has converged, temperature does not change in the solid, does not change in the gas, and you're good. So this is what's happening over time. And you see every time you have a small bump here, it's going from gas to heat transfer problem and back. And you see that after a certain time, let's say, you reach a point where the heat flux, which goes from the blade to the gas, the total heat flux is 0. It has to be at steady state because the flux cannot go to another place. So you heat up at one point, you cool at the other point. And at convergence, I think I have a movie here. Yeah, you can see the temperature in the blade now. So that's the solid temperature computed with the solver. And you can see that it converges slowly. You can see this thing is still changing here. And you have a very hot zone here at the tip. Here it's cooled, and here it's getting warmer again. And remember, this temperature adjusts as a function of the flow. The flow interacts with that. You can see here the temperature on the pressure side, which is this thing here. You can see the cooling holes and the temperature here. You can measure the temperature of the blade and compare it to experiments. That's what they call the cooling efficiency. And you see here the experiment and the LES, and it worked well except here. At the end of the ring, there's something strange going on between the two. And we believe we know what this is, but for the moment we didn't fix it. It's the problem of the interaction between the blades, which leads to this problem at the end of the blades. Now, let me show you another example also, which is related to entropy waves. We've been talking about entropy waves. An interesting question now on a case like this is what's happening if a hot spot interacts with this blade? What's going to occur exactly? And this is now a fully coupled problem. We're going to solve it in time by solving the temperature and the flow at the same time. So you see here this hot spot arriving. It's like an entropy wave interacting with the flow. Then this hot spot is kind of dissipated by the jet. And you see the temperature of the leading point here. It's going up, but it's going up by almost nothing, okay? A few fraction of a Kelvin. because again, this blade is massive. It's a big guy. The point is that if you repeat that at 1,000 hertz, then probably this temperature here will start going to a higher level. Okay. If you want really now to know what the real temperature will be, that really means that you will need to know, if you want to compute the temperature in this blade, you need to know what's coming here. You need to know exactly the temperature and the velocity profile, and that requires coupling the flow and the heat transfer solver. And we did it for this turbine here. I'm going to show you a coupled computation where we actually do all the flow here, and we do the heat transfer in the blade here, which is the highest temperature. So this is the one you want to compute. And here, since we started doing that, we said, okay, we're going to have to couple the LES solver with the conduction solver, which is called AVTP. And since we do that, we should also care about radiation, because radiation may change the game here, so we should account for radiation somehow. So how do you do that? Well, you need now to couple 3 codes, not only 2. And this is something I'm indicating here. There's a way to do that. If you need to couple 2 codes, those of you who are writing codes probably know what I'm talking about. You can take one code and make it a subroutine of the first one. Okay? Now this code is probably 500,000 lines. This one is 1 million lines. You can imagine getting this one as a subroutine of that one. Good luck. It's going to be difficult. And now if you have 3 codes, you should make the 2 codes subroutines of that one. It's going to be crazy. The way it's done now, and not everyone agrees on that, that's the French way, let's say the European way, it's we use a coupler. What is a coupler? A coupler is like building an electric line between 2 networks, and you exchange only the information you need to exchange. This coupler is called OpenPalm. It's an open source code, so you can download it if you want it. And what this coupler does for you, it tells you, okay, here you want to exchange the temperature on the blade. Let's just write a small file which writes that, and I will read it here. And this thing will write the heat fluxes, and I will give it to that guy. And you can specify how this thing works. So I will give you a more detailed description of that in a few minutes. But let's say that this tool, OpenPalm, allows you to run multiple parallel codes on one machine in a simultaneous way. And that's really quite easy. And we have in the world now maybe I get about 50 groups using this tool when they do multiphysics, because it's an open source code and it's working very well. So that's the uncoupled simulation where you just only do the flow. As we said before, you know, for the blade, you see all these hot passages arriving on the blade. That's going to change, of course, the results. And I'm going to show you 2 simulations now, one with a 2-code simulation, when you have combustion and conduction in the blade, and the other one, which is a 3-code simulation, when we do combustion, radiation, and conduction, everything at the same time. The blade we're using is normally like this one. We were not able to have the inside geometry. That's confidential information. So we replaced this geometry by a very simple heat transfer coefficient on the walls here. We said, okay, we don't know the inside. Let's just assume that we have some hot air here, and we can determine, for example, because it's cooled by air, we can determine the heat transfer coefficient on the wall, and we're going to write inside the blade that the flux here is heat transfer coefficient multiplied the temperature of the wall minus the temperature of the cooling air. We use law of the walls everywhere because this is a high Reynolds number flow, and if you would want to resolve all that, it would be quite difficult. So this is the evolution of the temperature of the blade versus time. After a while, the temperature stops moving. You go to convergence, and you can look at the temperature profiles on the blade. What's very important for people who do this design is to know the temperature of the surface here, of the pressure side and the other side, so that you can actually use it to compute stresses and determine if this blade is going to hold on or not. Now, I'm going to show now the results of these 2 simulations. I just want to point out that radiation here changes the flow in different ways. The first effect is that if you have radiation here, and you are sitting here on the blade, if you see the zones which radiate, of course, you have more heat flux. You know, radiation goes straight, okay? So that's a direct effect. But since most of the combustion takes place here, radiation doesn't take curves, okay? So this blade here will not see that much radiation from that point. However, there is an indirect effect, is that if you have radiation in this zone, it will change the mean temperature profile here. And by convection, it will change the heat on the blade. How it does that is very difficult to say. So this is the radiative result. And it tells you that there's about 5% of flux which is lost compared to the total heat release because of radiation. This is the zone where radiation is the most intense on average. And you see here that it leads to about 5% loss, which is about 50K. So I'm coming back to this 25K that they want, you know, in the turbine department. If you have radiation, or if you don't have radiation, it changes the temperature by 50K. So right away, you see that predicting temperatures within 25K is probably asking too much. Now, this is the fluxes due to radiation on the walls. And as you can expect, you know, it's only in the primary zone that you get a lot of radiation here. After that, you're cooling the gases, and you see that on the HPS, there's almost no radiative flux. So in other words, the direct effect of radiation is negligible. Now, there still are effects due to the indirect effects. This is the temperature here, plotted as a function of the distance along the blade. And you have two computations. One of them is without radiation, that's two codes. The other one is with radiation. And you see that when you add radiation, it's not that it's going to be colder everywhere, it's changing everything. So there are places which are colder and places which are warmer on the blade. And again, it's just telling you that you should include radiation, and the effect of radiation is not simple because it's changing the whole flow field, basically. And I didn't mention that, but here you have 200K. So here you have like 50Ks again. So this is more than the accuracy which is expected by the people from the turbine department. Okay, I will come back to this business of acoustic excitation in a second. Maybe I'll just say a few words about that now. Yesterday we've been talking about combustion instabilities. There's one thing also that we know is that heat transfer changes the mean flame, it's also changing the instabilities. How do we know that? Well, because people have looked at it. The people who do experiments in combustion instabilities, all of them will tell you when I start my burner, it's doing something, and then I wait, and it's doing something else. This happens in domestic burners, it even happens in an engine. We talked about hooting 2 days ago, that's the same thing. You know, when an engine is cold, some things may happen. So it really means that what is changing, it's really the wall temperatures. So the wall temperatures play a role. So we studied that in many cases. That's what the Munich group did. We did it at Surfax. And the reason for that is that there are zones where flames are extremely sensitive to temperature. You look here at a Siemens engine. In this zone here, whether this point is hot or cold will change the flame anchoring point, so it will change the results. So it's an open issue at the moment. Of course, the simplest thing would be to do a fully coupled computation. I just want you to give one example. When we always have a problem like this, we like to go back to a simple flame. I want to show you one flame, which is the IMFT flame again. So it's a simple Bunsen flame, very, very simple flame. The only thing we do is that we have installed on this flame a system to control the temperature of the walls. Okay? And this allows us to change the temperature of the flame holder. And when you do that, you can look at the flame by different ways. We can look at the flame with a CCD camera to look at the movement of the flame. And what we did also is that we installed an infrared camera on this wall here to look at the temperature of this wall, so that we could actually see what was the temperature of the walls and correlate it to what we would see on the flame. Now we use also a photomultiplier here to measure the unsteady activity of the flame. If there is a combustion instability, this thing will tell us. And we cool this system here from 1 to 95 degrees C. So we can control the temperature. So this is an illustration of what's going on. So we start the flame now. And as soon as we start it, you can hear the noise. The walls are cold for the moment. You can see the wall temperature. And then if we wait now, we increase the speed now. And you see the walls are getting warmer and warmer. The flame is stabilized just on this wall here. This is the side wall of this flame, okay? If you turn this image, put it here, you will have the temperature of the walls. And when the walls get warm, as you can see from the oscillations here in the emission, the flame gets stable again. And then, at this point, we started cooling the wall, so the wall gets cold again. And when the wall gets cold, the flame becomes unstable again. So in this experiment, there's a direct control of the instability by the wall temperature. So if you think about that in an engine, it will tell you if you take a gas turbine, you would start it. When the walls are cold, it would oscillate. And then a few seconds later, maybe 30 seconds later, it would stop oscillating. And then you can operate it. This is also why certain engines make noise at cold start. And then if you wait long enough, it disappears. There are fundamental reasons for that. There's actually there's a guy in the Siemens group, well, Ansaldo, actually, I should say. It's not Siemens in that case. Ansaldo group in Italy called Di Vita, and he has a big theory on that. And the theory basically says that if the walls of a combustor are cold, you're more likely to have unstable modes. And it's related to the Rayleigh criterion. Our experiment seems to suggest the same thing. So you can plot, you know, the pressure oscillations as a function of time. And again, those are decibels. So when you lose 20 decibels, it means the flame does not oscillate anymore. And you can see the evolution of this thing. So as soon as the cooling comes back, you have unstable mode. And if the walls are hot, then you have no problem. Okay. I want to finish today by another example of the importance of where am I now? Of cooling. And this one corresponds to something we did actually only a few months ago. Where am I? Okay, this guy. Okay, it's going to be also a very simple experiment. We like to do simple experiments when we can. And the issue here is to prove also the power of this reduced schemes that I've shown you before, to illustrate the coupling techniques for multiphysics, coupling codes, and to talk about heat transfer and combustion and flame stabilization issues. I haven't talked much about flame stabilization. I would say that flame stabilization is not the same thing as flame stability. Okay? Flame stabilization really means that if you design a burner so that the flame stabilizes here, either it will or it will not. Okay? If the flame is quenched, it's not stabilized here. If the flame flashes back, it's not. Now, once it is stabilized, it can be either stable, it doesn't move, or unstable, it moves. So flame stabilization is a different problem compared to flame stability. Of course, if you have no flame stabilization, you will not even be able to talk about the flame stability. So you need first to stabilize the flame. So we looked at a very simple question. You've seen in the previous talk that we showed that if you have a flame stabilized like a Bunsen flame, we looked at this flame, the temperature here controls the flame oscillations. So we looked at another problem which is observed. This is what you have, for example, in post-combustion. You stabilize flames on a bluff body, usually a cylinder. So you take a cylinder, you put it in the middle of a premix flow, and you look at flame stabilization. And an interesting question is, what's the influence of the temperature of the flame holder? How does it play a role in this problem? So to do that, we use the flame holder, and a very simple experiment that you can do easily. You inject methane and air. So here it's premixed. Here you laminarize the flow using glass balls and honeycombs, which also act, by the way, as flame arresters in case you have a flashback. Here, the whole section here is controlled and cooled so that we know exactly the temperature. And here you have one cylinder on which you stabilize the flame. And we can control the temperature of this cylinder. And we can either use a cooled cylinder or an uncooled cylinder. So when we cool this cylinder, we'll be able to keep its temperature to low values. So this thing here will be 300 K. And when we don't cool it, it will go to high temperature. Because, you know, nothing is there to cool it. It will go to 700 K. And the interesting point, again, is does that change the flame shape? Because, again, you go to FGM, FPI, flamelet. No one ever asks what's the temperature of the flame holder. We all act as if it was an unimportant quantity. Why? Well, because we cannot compute it. So we say if we cannot compute it, it's not important. Okay? So the French say, you know, it's like when you've lost your keys, you know, in your house, you search for your keys in the room where there is light. Okay? Because that's the only place where you can search. That doesn't prove the keys are there, you know. It's just that you do what you can. So here, I'm going to show you two examples. This first one is cooled. It's actually an interesting thing to set up. You have a bluff body here, a cylinder, that you inject water in the center, and the water comes back from that side. And this way, if you put enough water, cold water, you can keep the whole thing around 300 K. And as you will see in a minute, in that case, radiation will be important. So the emissivity of this cylinder is taken to be 0.9. We will account for the fact that this cylinder is losing heat, you know, towards the cold walls. When you do an experiment, everything I'm going to show you, we have done DNS and experiment side by side, so we know exactly what's going on. This is a view of the OH radicals here, or maybe it's CH. I'm not sure. We need to check, but anyway, it's the flame position. And you see that the flame position here is exactly at that point. When we looked at the previous one, that was the same information, you see here that the flame is much further away from the cylinder. So right away, between this case, which is cold, and this case now, which is uncooled, so which goes to high temperature, you see that the flame here is able to come much closer to this point. You can see actually here that there must be some flame hole interaction. And we actually, when we compute the flux here, we find it's of the order of this 0.3 times the power of the flame. So now we're going to compare this case, which is uncooled, with this case, which is cooled. Of course, the outside diameter is the same for both cases. Okay, we didn't change anything. So it's the same shape, same geometry. One of them has a cooled flame holder, and the other one is uncooled. So here, to do that, we used AVBP as usually, and we used this reduced chemistry, ARC, that we discussed 2 days ago. And here, we used a 13 species scheme for methane. We also used a 19 species. The results I'm going to show are for 13 species. Actually, for 19, they are much better. So the difficulty now is that you do this computation for the flame. You need to do something for the flame holder. So in the flame holder, we need to compute the temperature. So this is done with this code called AVTP now. And as I've said before, the time scales in the flow is about 50 milliseconds. And the time scale in the solid is about a few minutes. You know, the time it takes for the metal to heat up is large. You know that when you cook, you know, and when you put something on your fire at home, you put a plate here, you can leave your hand on it like for a few seconds. You know, it takes time for the heat to go through the metal. So for us, it's a difficulty because it moves that synchronizing these two things is going to be difficult. So we do that with this OpenPalm software. And if you type, by the way, OpenPalm on the network, OpenPalm Surfax, you're going to find this link to that. And this is what OpenPalm is doing. So OpenPalm is basically a higher level system which tells you, take code 1, code 2, and code 3, run all of them together, exchange the information you want, and you can even make tests. For example, you can look at a code and say, okay, this one's not finished, so I'm going to wait for this one to finish. And if they are converged, I'm going to stop. If they are not converged, I'm going to restart another one. So you can control. It's like a big, those of you doing Python, you know Python, you have all these scripts. It's a smart way of scripting the whole thing. Of course, to do this, you need first to, we call that palmerize your codes. What means in that case palmerize a code? It means, for example, here, the AVTP solver will write the fluxes on this surface, and the AVBP solver will write the temperature on this surface. You have here a methodology to interpolate between the two grids because they are not the same grids. The grid you use for the heat is not the same as the grid you use for the flow. You interpolate and you exchange. So here there's a place saying, here are the fluxes, here there's a place saying, here are the heat, the temperatures, and what Palm is doing is to exchange them in a method that you don't need to know. It's just working. So, of course, I did not discuss that too much. An important part of that, of course, is the interpolation of one grid to the other. That's a tricky part. You want it to be conservative. You want it to be fast and high order. That's done in the solver. And the license of that is LGPL for those of you who know open source code. So this is also the same methodology we use when you do a full engine, for example. If we want to compute an engine, we're not going to make one mesh. What we do is we make one mesh for the combustion chamber, one mesh for the first stage of the turbine, another mesh for the next stage, etc. And then we couple them with OpenPalm. So if you do, for example, a 10 billion points mesh, it's much better to do 10 times 1 billion and to assemble. Because, for example, today, most mesh generator systems will allow you to do 1 billion points, but not 10 billion. So you can do 1 billion. You can even run it first, and then when they are ready, you assemble them with OpenPalm. And that's a very interesting feature when you want to do this kind of simulation. How do you assemble them? If you do flow, for example, what you install is plugs on both sides of your system. This is AVBP. This is also AVBP. Both instances are running on the same computer, and they exchange information on this overlap zone here. That will allow you, for example, to beat this question of time steps. You know, if you have very small time steps here, and here you don't need very small time steps, then you can disconnect the two domains this way. That's one of the things we're doing right now. But that's not the topic. Let me go back to my flame here. So this is the interface between the solid and the gas. We use prism, well, actually EXA here on the solid, and then we use tetrahedra. And in the solid itself, then we use tetrahedra. And the exchange of information takes place along this line, and this is what's done with OpenPalm. So let's look now at the results of the DNS and the result of the experiment. So there's a small problem always when you want to compare experiments and simulation in terms of radicals, is that what is exactly measured in the experiment. In the experiment, this is OH, while in the simulation, it's really reaction rate. So they are not exactly the same quantity, so they don't have to be exactly at the same place. But as you can see, the lift-off distance here is very good, and the flame position and angles are quite good. So this is the cooled case. In the cooled case, we can compare the fluxes, and you see that the heat flux here coming inside this guy is of the order of 30 watts. The flame power is a few kilowatts, so there's not much heat going into the flame holder, but you need it to cool this thing. Now, if you look at the cooled case, you also have the temperature in the solid now. You see the solid is about 300 K here and 285 or something on that side because the water is at 285. And it's almost isothermal. You have here the heat release, here you have the temperature, and here you have the velocity. You see that the stabilization in a flow like this takes place in the recirculation zone. So the gases are recirculating, and this is the flame begins somewhere here. And then when you go far away here, you find a normal premix flame. Now, you see also that if you travel here along something which should be the flame, you have a zone here where you have no combustion. It's an extinction zone. It's a zone where flame-wall interaction is very strong. Then if you go far away downstream here, you find a normal flame. We compute here the adiabatic flame speed, and you see it's reaching 1, which means it's exactly as if you would be in a laminar adiabatic flame. And in the middle here, you have what we call a transition zone where you go from quenched to fully ignited. You can do cuts in the flow like this. You can look at a cut here and at a cut here. if you make a cut here on the CD line and you look at the fuel mass fraction, temperature, heat release, you recognize your classical premix flame. Okay? But if you do the same thing here, well, here fuel is only diffusing and temperature is only diffusing and there is no reaction rate. This flame is quenched. So there is premixed gases, but these premixed gases are too close to the cold zone, so they cannot burn. So it's a quenched flame. Now, when you don't cool this thing, then the flames come closer here to the cylinder. The temperature of the cylinder goes up by 400 K, which is, quite a lot. And in that case, the interesting thing is that this thing is hot enough that you need to start worrying about radiation. Why? Well, you will see in a minute that if you don't include radiation, you can have surprising results here. We did include radiation just by saying that this cylinder at 700 K would radiate to the walls here as if it was a gray gas with an emissivity epsilon, and we'll change epsilon. For the moment, we took 0.9. So this is the temperature profile in the uncooled case. As you can see, the temperature isocontours are like this, means that flux is entering here and leaving on the other side. There's about 60 watts here coming from that side, which is the hot side, and this 60 watts go into 30 watts by radiation and 37 watts by conduction. So the fresh gases here are cooling the cylinder, but the cylinder also gets cooled by radiation. And as you can see, this is about 2 times what we had for the cooled case. So the cylinder now gets much warmer, it gets more flux. Now this is the temperature profile with the temperature in the cylinder. There is no cooling system, now, so it goes from 700 to 698 because it has a high conductivity. It's almost isothermal. And you see now that the recirculation zones are gone. There's only very 2 small recirculation zones because the flame now is so close to the cylinder that it's much more viscous, so the recirculation zones are gone. I will show you in a minute how this takes place. So this is a comparison of the 2 flames, So they are very different. And again, it's a striking result because in most models, we don't care about the temperature of the flame holder. Actually, when you write FPI, you write a tabulation, you start by saying, this is not important. I don't want to know about it. Well, in practice, it's changing things. So this is the cooled case. The flame is farther away from the cylinder, and it's stabilized in the recirculation zone. Here it's the uncooled case. The flame has been able to come here, and it's giving no recirculation zone, almost no recirculation zones. A small one here and a small one there. So again here, if you look at the temperature profiles along a line here, which is the flame, you have a quench zone, which is very small. You have an adiabatic zone here. And here you have an interesting zone here when it burns more than the adiabatic flame. You see this zone here, it's actually more intense than an adiabatic flame. So it's really telling you that there are some things happening in these zones which are not predicted, cannot be predicted with an adiabatic formulation. So the cuts are the same as before. You have here a normal flame, and here, even very close to the cylinder, you still have a burning flame because now the zones, the cool zone here is much smaller. So in terms of flammable interaction, you have to be very close to the cylinder before you sense the fact that you have heat losses. Now, that's a cute movie, as you will see. We have plotted here the streamlines. Here is the flame position, and here is the temperature. And we're going to go from a uncooled situation to, well, actually it's the other way, from cooled to uncooled. So this is what you have for the cooled case. And so we run the simulation by slowly going to the cooled case, the uncooled case. So this is the cooled case. And now, as you can see, we stopped cooling. So the flame moves slowly, slowly back, and the recirculation zones go away. And then we end up with this flame, where now there's only 2 recirculation zones. And you can see that there's really not much in common between these 2 states. So you have to account for heat losses when you do this kind of things. Okay, now it's finished, and now it's another stable point, which really means that we need to account for these things. Now, just to finish, what about radiation? I want to show you something now, which is the following. That's the flame position as a function of the emissivity of the cylinder. If you're not careful, and what may happen is that if you have a lot of radiation, the cylinder is cooled, relatively cold, and the flame is here. But if you decrease the emissivity, the cylinder cannot cool itself, and what the flame is doing, it's creeping up here. It's finding more and more places to come here. And then suddenly, at an emissivity of 0.15, the flame jumps ahead of the cylinder. So now that's a very strange situation where the flame is stabilized upstream of the cylinder. And that's the shape of the flame you obtain. Now the cylinder is swimming in burnt gases and the flame starts upstream of it. Now, of course, if this happens, and we've done experiments where it happens, this thing will go away fast, okay? Because now it's going to very high temperatures. The only way to prevent it to go to high temperature in the simulation is to account for radiation. Otherwise, it would go to the adiabatic flame temperature. We know it's not melting right away. We cannot operate for more than a few minutes. But that's also telling you something else. If you want to be precise now, you have to include radiation. And it's a problem because we don't know the emissivity of this guy. The emissivity of this cylinder here depends on how old it is. Because when it's new, it has a small emissivity, but if you wait, there's a little bit of soot comes on it, emissivity goes up. So that really means, again, that if you wait long enough, the flame position might change to the point that you might jump in front of the flame holder. Okay, I think that's, yeah, okay, that's just the difference between 0.1 and 0.15, okay? 0.15, you're still normal, I would say, but 0.1, you're not. Okay, so that's all I wanted to say for this morning. If you have questions, we can take them now.
When did you have instability for the uncooled one or the cooled one?
None of those are unstable for that case, okay? Because the acoustic tuning is such that they are all, these two flames are stable. What's true, however, if their flame transfer functions are different. If you send an acoustic wave on this one, you have a different response from that one. So that's telling you that the unstable modes will also be different. But for this case, when we operated, we tuned the length of the combustor so that there is no instability.
What I recently read by a paper, as the first unwork, is that when there is two recirculation zone which you have for the cooled, for the uncooled case, so you have two recirculation zones. But for the cooled case, you have one recirculation zone. So the stagnation point is shifting. So please say in this paper that that's an indication of systemic instability.
That's the MIT paper, you mean?
Yeah.
Yeah. The MIT was on a square, that was a square flame holder, which is a little bit more complicated than that one. But clearly, it's true that whatever you have, if you change the flame position, the flame transfer function will change, the instability will be different. That's clear. Except that in this case, we stayed in a stable regime, so there is no problem. Yeah. OpenPalm is an ensemble of Python scripts which allow you to run many codes at the same time and to do data exchange between codes so that you don't have to put one code as a subroutine of the other one. You just have to exchange, for example, heat and temperatures. And the code will do that for you. And then it will monitor how you run the two codes at the same time on the parallel machine. This code comes from the global change community. You know, when you do global change computation today, you can predict the weather, not the weather, you can predict the climate only if you couple the ocean and the atmosphere. And the ocean codes are huge and the atmosphere codes are even bigger. So you cannot make one subroutine of the other. So you exchange things at the interface, which is the sea surface and the ground. And so you continuously exchange information between the two codes. This is where couplers are used. So we use the same now for CFD for us.
We have to write another subroutine for interpreting the meshes, or it comes separately?
No, the interpolation of one grid to the other is also done in OpenPalm. They do that for you with high order schemes, which is the other problem. You really need to conserve, because the meshes are not the same on both sides, so you need high order interpolation between the two meshes. So you have surface interpolation, you also have volume interpolation, depending on how you couple your codes.
The radiation
Yeah.
Are there any cases where you think that radiation from food is also important and should be
Sure. In that case, it's a non-sooting flame. Even in a non-sooting flame, as you saw, that we have a 50K difference. But if the flame would be sooting, then it would be much more. The radiative heat flux will go up, and then it will change things even more. This case was not sooting.
in general we do not have models accounting for the radiation from food?
Well, for soot, it's true, but there are some. If you give me the soot volume fraction, I can have a reasonable model for soot emission. Let's say that if you have the volume fraction, going now to the radiative flux is not as difficult. There are some the people working on radiation, they have some models for that. The weak part is to get the volume fraction. But if we have it, we have some crude models to do it.
So is there critical condition or some criteria when we can see the flame upstream or downstream? Because we just proved that in certain conditions the flame does attach to upstream of the work body.
Yeah.
Is there a certain condition when we can distinguish, okay, after that it will go upstream and it will affect the condition?
Well, we don't really know yet. We don't know that for the moment. We know that if the radiative flux is too small, there's the possibility for the flame to go upstream. And we saw it in the experiment. How important it is in practice, we don't know, because it depends on the shape. I don't know. I don't think if MIT finds, yeah, I think the MIT group, they don't see upstream stabilization. Or maybe they do, actually. So normally it's really something you don't want, okay, because that will kill the flame holder anyway. So we need to avoid this kind of behavior. But clearly, to predict it, you need radiation.